Good morning, everybody. Today we are going to discuss low chatellier principle. Okay, what is low chatellier principle and what is it's all about? Low chatellier principle, it is a principle that express the effect of the factors of the rate of the chemical reaction on a reversible reaction. Again, so the aim of studying low chatellier principle is to study the effect of the external factors on an equilibrium system. Okay, so what it does states about if an stress is applied to a system at equilibrium, means if there is something external affect an equilibrium system, like changing the concentration, changing the temperature, changing the pressure, okay, probably it would affect the equilibrium. Okay, يعني for example, if we are in environment, in ecosystem, okay, and suddenly there is drought waves, okay, this would affect the change, the amount of rains that falls on this ecosystem, okay. So for also a chemical reaction that consider an equilibrium system, any external factor, any stress is applied to this system will affect the reaction, تمام, or will move the reaction in the direction that will relieve that stress, or in the direction that will reconsider balance and re-establish the equilibrium once again. Okay, يعني for example, if you did something wrong with your computer, you press undo. Okay, so how could low chatellier principle be applied on an equilibrium system? Okay, first, let's study the factors that affect the equilibrium. First, concentration, temperature, pressure, and catalyst. Okay, concentration, number one, the effect of concentration. Number two, the effect of pressure. Number three, the effect of temperature. And number four, the effect of adding a catalyst. Okay, first of all, let's start with the effect of concentration. Okay, if we look at the effect of concentration, okay, increasing the concentration will shift the reaction to the opposite direction. Again, changing the concentration will direct the reaction into the opposite side. Yani for example, if you add more reactant, you will be shifted to the right, means to the product side. Or if you increase the concentration of product, you will be directed to the backward side, okay, or to the left side. So if we add more reactant, like what's written here, you add more reactant, you shift the reaction in the direction of increasing the product percentage. But if you remove the reactant, mean it's not there, then the reaction will return back in the backward direction to regain the lost reactant. Okay, but what about the product? If we add more product, it will shift the reactant to the left side. It shifts the reaction to the left side or the direction of regaining the reactant. And if you remove the product, it will shift to increasing more product. Okay, let's try here. Okay, let's look at this chemical reaction. We have this Haber-Bosch reaction, whereas nitrogen plus hydrogen gives ammonia gas. Okay, hence you see the sign, you know that it's a reversible reaction. Okay, but let's remember, what is a reversible reaction? It's a reaction that proceeds in both ways, the formation of reactant and the reformation of product. Okay, how can we differentiate it between it and a complete reaction? A complete reaction, one of the product left the reaction vessel, like in the form of precipitate or evolved gas. Okay, right. Here, let's see what will happen if we increase the amount of nitrogen. Okay. What happens if we increase nitrogen concentration? Okay. First, nitrogen, it's in the reactant site, also as hydrogen, but ammonia, it is in the product site. Okay. What happens if we increase the percentage of nitrogen? Nitrogen, it's in the reactant site. So if we added more nitrogen, the reaction will proceed in the forward direction. Again, if we increase the percentage of nitrogen, this means the reaction will shift it in the forward direction or to the right side, in the direction of increasing our formation of ammonia. So if I pushed here, I added more nitrogen, the reaction goes in that direction. So what will happen to ammonia percentage and hydrogen percentage? Okay. Since we go forward, this means the percentage of ammonia gas will increases. Again, the percentage of ammonia gas will increases, okay? But if we look at hydrogen, hydrogen, it's one of the reactant. Since nitrogen will be consumed or will be converted into ammonia, also hydrogen will go in the reaction and is in the direction of formation of ammonia. This means that the percentage of nitrogen, since it's consumed, the hydrogen also will be consumed. This means hydrogen will get decreased. Okay, again, why hydrogen decreased? Because it's in the reactant side. Okay, and we are going in the direction of making ammonia. It's like you are making sandwiches. You get cheese, you get bread. If you are proceeding in making cheese sandwiches, then both of cheese and buns will be consumed, but the number of the cheese sandwiches will increase. Okay, so again, if we are moving in the direction of the product, so means that both of the reactant will be consumed and the percentage will decrease, and the percentage of the reactant will the percentage of the product will increase. Now, what if we removed nitrogen? Means there is no nitrogen, okay? I remove nitrogen. So the reaction will proceed in direction of reformation of nitrogen. So this means the reaction will go backward, okay? The reaction will go backward direction, okay? Right. So what is the effect on hydrogen and ammonia? The effect on hydrogen, since I'm going backward in the formation, in the direction of breaking of ammonia to restore nitrogen gas. So if I'm going to break ammonia, so this direction is formation of ammonia in the forward direction, and in the backward direction, it's a breaking of ammonia or decomposition. So if I'm going backward, this means I will restore hydrogen as well as nitrogen. So this means the percentage of hydrogen will increase. But since ammonia is being broken down into nitrogen and hydrogen gas, this means its percentage will decrease. Okay. What if will be the effect on changing the concentration of the product? Okay. Right. What happens if I increased the percentage of ammonia? Okay. Again, increase the percentage of ammonia. What will happen? If I increase ammonia, which is in the product side, this means I'm giving the chances for the backward reaction to initiate, because increasing the concentration will shift the reaction in the opposite side. So this means the reaction will shift it to the backward side or to the left side. This means both of nitrogen and hydrogen will both increase. And ammonia, of course, will be consumed. And since I'm talking about ammonia, so I'm not considering it as an effect on itself. But what happens if I remove the ammonia gas? If I remove the ammonia gas, then the reaction will proceed in the direction of restoring again this ammonia. So this means the reaction will shift into forward. Okay, again, so if ammonia is removed, this means the reaction will move in the direction of restoring that ammonia. So this means both of nitrogen and hydrogen will be consumed, so their percentage will be decreased, and I'm regaining ammonia gas, so its percentage will increase. Okay, so this is about the effect of concentration on an equilibrium system. Okay, let's move to another point. What would be the effect of temperature? Okay, again, the effect of temperature. When we talk about temperature, we have to differentiate between endothermic and exothermic reaction. Again, we have to differentiate between endothermic and exothermic reaction. Okay, first, let's study the effect of temperature on an equilibrium or on a reversible exothermic reaction. Okay, what's an exothermic reaction? It's a reaction where heat is released to the surrounding. Again, it's a reaction where heat is released to the surrounding. Okay, so this means heat is part of the product. Okay, again, heat is part of the product. Okay, so what would be the effect of increasing the temperature? Okay, so if we add heat to an exothermic reaction, this means like I'm giving back one of the product. Okay, again, it's exothermic reaction. It's releasing energy. So if I gave energy again back to this system, this means the system will move to the backward side. Okay, so again, it will shift in the direction of the formation of reactant, or shifted to backward side. Okay, so again, adding heat to an exothermic reaction, this means the reaction will shift backward or to the direction of the formation of reactant. But if we removed heat or we cooled this reaction, this means I took heat, so it will move in the direction of producing heat again. So it will be shifted into forward direction. Okay, how can we know if the reaction is exothermic or endothermic? This will be regarding the change in heat content, okay, or the change in the enthalpy. The first sign, we would find the heat as one of the product. Okay, this is a sign that it's an exothermic reaction. Or we could find the value of enthalpy delta H equal negative, for example, hypothetical number 92 kilojoule per mole. Okay, so since the enthalpy or the delta H is in negative value, this is exothermic. When we see the heat is part of the product, is exothermic. Okay, so increasing the temperature, what will happen after increasing the temperature? The reaction will shift to backward. Okay, again, reaction will shift backward. Okay, this is about increasing temperature. So what will happen to the concentration of ammonia, hydrogen, and ammonia, nitrogen, hydrogen, and ammonia gas? Okay, since I'm proceeding in the backward direction, so ammonia will decrease. Sorry, at all. Again, since we are moving in the backward direction, ammonia percentage will increase as well as hydrogen. But again, nitrogen percentage and hydrogen percentage will increase, but ammonia percentage will decrease. Okay, Again, nitrogen increase, hydrogen increase, but ammonia decrease. But if we decrease the temperature, this means the reaction will move into the forward direction. And since it moved forward, the ammonia percentage will increase, but nitrogen and hydrogen will be consumed, so the percentage will be decreased. Okay, this is if it's an exothermic reaction. What if it's an endothermic reaction? This means that the heat is part of the reactant. Okay, again, heat is part of the reactant. So increasing heat will probably shift the reaction to the forward direction or in the direction of formation of the product. Okay, but cooling the system or removing heat, this means the reaction will proceed in the backward direction. For example, if we have hydrated copper sulfate, okay, CuSO4 dot 2H2O, the hydrated blue copper sulfate, okay. But what happened if we heated the blue copper sulfate? This means a thermal decomposition will happen to it and they change into anhydrous copper sulfate, which has a white color plus water. Okay. Right. So since I gave heat to this reaction, it's an endothermic reaction. So increasing the temperature, this means the reaction will shift to forward direction, and the color will change from blue to white. Okay. But decreasing the temperature will shift the reaction into backward direction. Okay. So this is the effect of heat on an endothermic reaction. Pressure. Okay. Pressure only affects gases. Okay. So if there is a gas is in one of the reactant or product or both of them, this means pressure could be applied. Increasing or decreasing the pressure means changing the size of the container vessel. Okay, so if I have high pressure, this means we have, suppose we have a piston. Okay, so if I have a high pressure, this means I have a small reaction vessel. Okay, so if this is a piston, okay, and it's plugged, this means the molecule have fewer volume to do the reaction. So again, high pressure means small reaction vessel or small volume, but low pressure means big volume. Okay, again, increasing pressure means decreasing the volume of the vessel, but decreasing pressure means increasing the size of the vessel. Okay, pressure will only affect if there is unequal number of moles of gases, of reactants and product. Okay, for example, if we look at this chemical reaction, okay, of producing of ammonia, we have a reaction between nitrogen gas, hydrogen gas, okay, and producing ammonia gas. Now, what happened if pressure increased? Okay, first, if we want to determine the effect of pressure, we have to count the number of moles of gases in both sides, okay, to see if it's equal or unequal. Again, we have to see if it's equal or unequal, okay. So on the reactant side, we have 1 mole of nitrogen plus 3 moles of hydrogen, means we have a total of 4 moles of gases. Okay. So in the reactant side, we have 4 moles of gases. But on the product side, we have only ammonia and it's 2 moles. Okay. So what will be the effect of increasing the pressure? Increasing the pressure will shift the reaction in the direction which contains the least amount of moles of gases. Again, increasing the pressure will shift the reaction in the side with the least moles of gases. Okay, so here in this reaction, we have 4 moles on reactant side and 2 moles only a product side. So increasing the pressure will shift the reaction in the direction of making ammonia. Okay, again, increasing the pressure will shift the reaction in the direction of making ammonia. So increasing the pressure, the reaction will be forward. Okay, so this means we're having more ammonia gas. But what if we decrease pressure? Decrease pressure, so we will go to the side with the least number of moles. So if we decrease pressure, this means we are going backward. Okay. So here we have 4 mole of reactants, gases, and 2 mole of product. Thus, the reaction will shift in the direction of producing ammonia. Okay. Here, another example. BCl5, phosphorus pentachloride, okay, plus decomposes into phosphorus trichloride and chlorine gas. On the reactant side, we have only 1 mole, okay, and on the product side, we have 2 moles, okay. So this means if I increase the pressure, this means we will proceed in backward reaction. Again, why backward? Here we have only 1 mole of gases, but here we have 2 moles of gases. So increasing the pressure goes to the least moles, so we go backward. But decreasing the pressure will shift the reaction in the forward direction. Again, 2 product gases versus 1 reactant. So if I want to proceed forward, we have to decrease pressure. Okay. The last one is catalyst. What is the effect of catalyst on equilibrium system? Okay. A catalyst lowers the activation energy, which means the rate of the chemical reaction increases. Okay. So it will lower the activation energy for both forward and backward reaction. So this means changing or adding catalyst doesn't affect the equilibrium. Okay. So again, adding the catalyst doesn't affect the equilibrium. Okay. So we have a question here. We want to apply on what we have learned in this lesson. Okay. Here we have sulfur plus 12 oxygen gives sulfur dioxide gas plus 808 kilocalories. Okay. What will happen to the chemical reaction if oxygen gas is added? Okay. Oxygen is added. Let's check where oxygen is. Oxygen, is it in the reactant or the product? Oxygen is in the reactant side. So, okay. So what happens if the oxygen gas is added? So we have 4 or 3 conclusions. Okay. Number 1, since we are increasing the percentage of one of the reactant, then the reaction will goes in the forward direction. Okay, so number 1, the reaction goes forward or in the direction of the formation of sulfur dioxide. Number 2, What will happen to the amount of sulfur dioxide gas? The amount of sulfur dioxide gas will be increased since we are going in forward, so the percentage of the sulfur dioxide will increase. Number 3, the third conclusion, what will happen to sulfur itself? Sulfur will be consumed, so sulfur percentage will decrease. Okay, يبقى sulfur will decrease. طيب. Number 2, the reaction vessel is cooled. Okay, cooled. What is meant by cooled? This means the temperature decreased. Okay, again, temperature decreased. If we are considering temperature, we have to look if this reaction is endothermic or exothermic. Here we have sulfur plus oxygen gives the sulfur dioxide plus heat. What we say when we find heat in the product, this means it's an exothermic. Okay, so this reaction is exothermic reaction. So when the reaction vessels is cooled, means temperature decreased. And when temperature decrease for an exothermic reaction, we removed the heat, the reaction will go in the direction of restoring heat. So this means, number 1, the reaction will be forwarded since it's exothermic. Number 2, both sulfur and oxygen will be consumed, so their percentage will decrease, while the percentage of sulfur dioxide will increase. So this is the effect of cooling this reaction. What will happen if the size of the container is increased? Okay, size increase or volume increase means pressure decreased. So again, we said volume is inversely proportional to pressure. Okay, right. So if a pressure, let's count the number of moles. On the reactant side, we have 13 moles. Okay, and on the product side, we have 8 moles of sulfur dioxide. Okay, a total of 13 here and 8 on the other side. So decreasing the pressure will shift the reaction to the higher moles. So this means that the reaction will be shifted backward. Okay, again, pressure decreased, go to the side with more moles. So this means the reaction will be shifted into the backward direction. Right. What will happen to the sulfur dioxide and sulfur and oxygen? Since it's backward, sulfur and oxygen increases. We are restoring them, while sulfur dioxide decreases. What is the effect of if sulfur dioxide is removed? Okay, sulfur, I'm sorry, it's trioxide, not dioxide. I'm sorry, my bad. Sulfur trioxide is removed. This means we are removing the product, so the reaction will proceed in forward direction to restore sulfur trioxide. Okay, so this means both of sulfur and oxygen will be consumed and their percentage will decrease, while sulfur trioxide production will be restored, so it will increase. And the last one, catalyst is added, so no effect on equilibrium.